Hi everyone, welcome back. What I'd like to do in this video is take you through the material we would have gone over in class today had we had class, which is going to be on carbon-13 nuclear magnetic resonance, or NMR spectroscopy. We've already gone over a few types of spectroscopy. We've gone over IR. We've also gone over mass spectrometry, which again, technically really isn't a type of spectroscopy. It's a different type of method. The two NMR methods we'll discuss, namely carbon and proton NMR, are much more powerful than IR spectroscopy and give many more hints as to the structure of a compound than your average IR spectrum. And certainly the most powerful way to use spectroscopy of all of them is to combine all of these. And at the point where if you have all of the spectra of a compound, you can pretty much tell what the compound is. That comes later though. We'll bring all that into play after we've learned about proton NMR spectroscopy, much later on in the term. So I don't want to spend a lot of time on the theory behind NMR or what all the parts in a nuclear magnetic resonance spectrometer look like, or drawing a beautiful diagram of it, or exactly how Fourier transform works. I don't think this is really that important for us to understand. I want to keep this material just as I have with IR spectroscopy. I want to keep it very results-oriented and very practical. First of all, why should you care about carbon NMR spectroscopy? Well, let me just make sure I'm sharing my screen here. First of all, NMR and a method that you'll use probably later on called MRI, those are basically the same phenomena, and the guts of the two instruments are basically the same. It's just, as you can imagine, they didn't want to use this scary word nuclear in something that's going to be used in medical imaging, so that's why they called it magnetic resonance imaging. But they're both the same type of phenomenon. They both use the same type of phenomenon at the level of atomic nuclei. And then I think another thing that's very valuable to students about learning spectroscopy is that it allows you to practice what it's like making a diagnosis given a patient who comes in with a whole set of symptoms and conditions, and some of it seems to contradict itself, but you've got to put it all together. You know, none of it looks exactly like what was in your textbook or what your professor told you, but you've got to put it all together somehow and come up with a diagnosis that makes the most sense. And solving spectra is very much like that, I think. So as I said, I don't want to spend a huge amount of time on the theory, but I also don't want you to be completely ignorant of it. And I'd like you to at least understand where the phenomenon comes from. It's a little more abstract, maybe, or a little more abstruse, maybe, than for IR spectroscopy, because there we could understand, at least at some level, the molecule absorbing a photon of infrared radiation undergoing some kind of vibration. This is a little bit more removed from our daily experience, maybe, but I just want to let you in at least on the basics of where the phenomenon comes from. Where it comes from is that all atomic nuclei, regardless of what element, all of them have a property known as nuclear spin. And what that means is that the nucleus has this property by which it behaves as though it were a tiny, rigid, rotating sphere. It isn't really, of course, but it is a property that makes it as if atomic nuclei were like that. And when you've got a sample of some compound, all of these nuclei and their spin vectors, if you will, are pointing every which way until we put an external magnetic field to it. And it's been a hot century since I've taken physics, but if I recall right, the symbol for a magnetic field is B. And when that happens, now all of the nuclei have only two possible spin states, either directly parallel to the magnetic field or 180 degrees opposite, anti-parallel to the magnetic field. And when we take an NMR spectrum, what we're measuring is the energy that it takes to flip a population of nuclei that are in the parallel state to the anti-parallel state. And yes, then we could talk about it decaying and all that sort of thing, you know, that it goes back to parallel slowly. I don't think that's anything we really need to concern ourselves with here. But the point is that you can flip any given atomic nucleus from the parallel spin state to the anti-parallel spin state. And when you do that, that requires the absorption of a really, really small amount of energy. I'm trying to see if I can actually never remember which is flip horizontal and which is flip vertical. Obviously, it must be flip vertical. So there, I just flipped that one nucleus from parallel to anti-parallel. And the amount of energy that it takes to do that is very, very low. It requires electromagnetic radiation in the radio wave range. That's in the far long wavelength or low energy end of the electromagnetic spectrum. And when that happens, of course, just very much like in infrared spectroscopy, we get a peak there that we could say it took this much energy to spin flip our nuclei, or maybe, if you will, since energy is proportional to frequency, you know, the frequency of radio wave photons that did that for us is so many hertz. And that would be fine, except there's one more complication. Luckily, it's one that's easily dealt with, which is the energy is of that transition going from parallel to anti-parallel is not completely independent of other factors. In particular, it does depend on the magnetic field strength of the instrument, which can vary. And we want a way of being able to take an NMR spectrum on any NMR spectrophotometer and get the same data out at the end, or at least get equivalent data out at the end. And so rather than using hertz to tell us where the peaks in our spectrum are, what we do is remove that dependence on the magnetic field strength by dividing all along the horizontal axis, and the instrument does all this automatically for us, of course. But at any given place in the horizontal axis, we're dividing that frequency of radiation absorbed by the magnetic field strength. And if you work it out, you get, in terms of units, hertz divided by megahertz, which just leaves you with a million in the denominator, since mega is a million. So that's where these units come from, parts per million. That's how we measure where peaks in an NMR spectrum show up. We say they occur at this or that number, this or that many parts per million. And the typical range of parts per million depends greatly on the nucleus. In carbon-13 NMR, I think you'll find typical chemical shifts are going to be from 0 up until round and about 210, 220 parts per million. For proton NMR, which we'll get to later, that range happens to be much smaller. They're from 0 up until maybe 14 or so. And if it were another nucleus like boron 11, then it would be yet another. Then it would be another range. Of course, organic chemists focus mainly on carbon and hydrogen, since they're the most common elements in organic compounds. But pretty much any element is going to have at least one isotope that's NMR active. And in my life, I've taken boron 11 NMR spectra. That works quite well, actually. I believe I've also taken lithium 7 NMR. So it could have been lithium 6. Both of them are possible. And then there was the horrible time I tried to take a sulfur 33 NMR spectrum. More on that later. But what do we mean by NMR active? And why am I suddenly talking about carbon-13 all of a sudden? Well, it's because for reasons that are well beyond the scope of this class, we can't really explain the reason why without using quantum mechanics and things like that. But as it turns out, in order for a given nucleus to be NMR active, one of two things must be true about it. If the element that the nucleus belongs to has an odd atomic number, and remember, you'll always be given a periodic table, of course. But if it is an odd atomic number, then all of its isotopes are NMR active. And then, as you can imagine, we generally pick the one that's easiest to detect, which is usually, maybe not always, but usually the one that's most common. So for instance, if we're looking at hydrogen, proton NMR uses hydrogen 1 nuclei. That's by far the most common type of hydrogen in the universe. Around and about 99% of all hydrogen in the universe is hydrogen 1. There is some deuterium, which is hydrogen 2. And as it turns out, it is possible to take a deuterium NMR spectrum. I have fortunately never had that pleasure, but it can be done. Proton NMR spectra are very easy to take because of the high natural abundance of hydrogen 1. What about carbon? Well, whereas hydrogen is element number 1, that's an odd number, carbon is element number 6, so its atomic number is even. And in cases like that, then the nucleus is NMR active only if the mass number is odd. So with carbon-12, which is again by far the most common type of carbon in the nucleus, 99+% of all carbon atoms in the universe are atoms of carbon-12. Well, that nucleus is inactive to NMR. You can't take an NMR spectrum using carbon-12. That's why we need to use carbon-13, which although it has an even atomic number, has an odd mass number. And so carbon-13 is NMR active. And just like, just as with hydrogen-2 that we call deuterium, deuterium is not radioactive, by the way. It's a stable isotope, stable heavy isotope of hydrogen, just has an extra neutron in the nucleus, 1 neutron as opposed to 0, right? Well, it's a similar thing with carbon-13. There's just 1 more neutron in the nucleus than for carbon-12. Of course, if we change the number of protons, then you change the element, right? When we get to different isotopes, we're looking at different numbers of neutrons in the nucleus. Just to give another example, if you wanted to take a sulfur NMR, you couldn't do it with sulfur-32 because sulfur is element number 16, and so the one with the even mass number, sulfur-32, is not active in NMR. You would need to take a sulfur-33 NMR spectrum, which I tried once, and I want to keep it brief, but I can tell you that all I got was a peak with basically a peak width comparable to the entire field width. It was just this, broad, shapeless peak that did me absolutely no good whatsoever. Oh well, so you win some and you lose some. To give another example, though, fluorine NMR is used quite a bit. Fluorine, I believe, is element number 9, and so it's going to be NMR active. The major isotope of fluorine is NMR active, and fluorine NMR works quite well. I've heard of nitrogen-15 NMR being done. That works pretty well. Phosphorus-31 NMR works quite well if you have a compound with phosphorus in it. Just like you wouldn't take a boron-11 NMR spectrum unless you had a molecule with boron in it. Otherwise, there's no point. Of course, we're going to focus on proton and carbon NMR. And we're going to start with carbon NMR because, trust me, it is much, much less complicated than proton NMR. So I think that's about all we need to say to get started here. Mostly what I want to do in class time today is show you a bunch of carbon NMR spectra so that you can know what to expect. A little bit more on chemical shift. It has to be relative to something. You have to have some kind of standard. And the most common standard used is tetramethylsilane, which is essentially a silicon atom with 4 methyl groups. And as you can see in this molecule, sometimes they abbreviate it TMS, by the way, but as you can see, all 4 carbon atoms are the same. The way we know that is because if we replaced, or you could also say all 12 hydrogens are the same too. You can replace any one of those hydrogens with, say, a chlorine, and you'd get the same compound. So the standard for carbon NMR is tetramethylsilane, where we set it by definition. We say that tetramethylsilane shows up at 0 parts per million, or most NMR solvents have a little bit of tetramethylsilane in them, and so we simply find that peak and we say there's 0, and then everything else is measured relative to that. And by the way, tetramethylsilane is also the most common standard used for proton NMR. We'll do the same thing with that one. All 12 hydrogens are equivalent. We find out where they show up and we say that's 0, and everything else is then relative to that. And yes, you guessed it, tetramethylsilane is also very commonly used for silicon-29 NMR, which is sometimes used by people who do a lot of silicon chemistry. So the nice thing about carbon NMR spectra is that in general, what you get is a set of nice sharp peaks, and one for each chemically distinct type of carbon atom. And I've left in your class notes here a step-by-step method that you can use when looking at a structure to know whether any 2 carbon atoms are chemically equivalent or not. So we talked about that back in chapter 10, and it still works just as well here. So let's see, what else? Before we go into actually looking at spectra, I do want to point out that there is a correlation table for carbon-13 chemical shifts. In an ordinary semester, I would simply say you will not be given that on exams. But at the same time, just like with IR, I do not recommend that you memorize it. Now, you'll be able to leave your book open to that page if you want to. But I will say, to the extent that you memorize that table, or to the extent where you try to check every single peak on that table, I would say either way you're wasting your time. Those ranges are only guidelines. They're only approximate values. They're not the be-all, end-all. And I'm going to recommend for carbon NMR that you do exactly like you did with infrared spectroscopy. Namely, that you get in there and look at a bunch of carbon-13 NMR spectra. I recommend that same website that we discussed earlier. That's the best advice I think I can give you. But having your book open to that page will not save you if you don't really know what you're looking at in the carbon NMR spectrum. Just as memorizing that table would not save you. I think either of those things is pretty much a waste of your time. So what I'm going to do here is just go through several carbon NMR spectra with you and give you an idea of what to look for and what you will commonly see in a typical carbon NMR spectrum. So let me improve my window over here. Oh no, I guess I really will need ChemDraw, at least in principle. I mean, I think a lot of these are going to be pretty easy compounds, but let's start with the spectrum of 1-pentanol. As you can see, we've got our horizontal axis labeled in parts per million. Would have kind of been nice if they'd expanded it for us so that the peaks are a little easier to separate visually. But I think you can see that we have 5 nice, sharp, clear peaks in this range. My goal in the exam, by the way, would never be to try to trick you. If there were 2 or 3 or 18 peaks that fell right on top of one another very close, I would tell you that. I would expect you to be able to look at this and say that there's 5 peaks. And that's not surprising. What's the structure of one pentanol? I think you know that. It would just look like this, right? It's a 5-carbon straight chain alcohol. And I think you'll agree, using the step-by-step method that's in your class notes, I think you can convince yourself that all 5 of those carbons are different. The methyl group certainly is unique. And then you have 4 CH2s, but they're all chemically different. This CH2 is attached directly to the OH. This one is not. It's 1 carbon further out. That one 1 carbon further out still. So none of those, no 2 of those CH2 groups are exactly the same as each other. So since there's 5 different types of carbons, we would expect 5 peaks, and that's exactly what we do get. See, that's the nice thing about carbon NMR. It's much less cluttered and much clearer to interpret, as you'll find, than proton NMR. There are several other cans of worms with proton NMR. That's why I'm putting it off as long as we can all get away with it. In terms of the chemical shifts, one thing is that very roughly speaking, the more electron density is around the carbon nucleus in the form of, or the more electron density is, as they call it, shielding that nucleus, then the further towards the right the peak will be. We call this end the shielded end, or the upfield end of the spectrum. And so the more electron density is shielding our carbon-13 nucleus, the more upfield it is. As you go further and further downfield, or further and further to the de-shielded end, now you're seeing carbon nuclei that for one reason or another have electron density withdrawn from them, either by pi bonds or by electronegative elements or something like that. And the exact correspondence to electron density around the carbon and where it shows up on the parts per million scale is even still not very well understood. There's some black magic there. But I would say, at least roughly, there is some correspondence there. And so what we seem to see is these 4 peaks that are all very well shielded, very much in the alkane range. Our most de-shielded one of them all is, what do you want to call that? 37 parts per 36, wait a minute. Well, maybe we'll call that 33 parts per million or something like that. These are all still pretty typically in the alkane range, except for this one up here, which is now, maybe we'll call that 62 or 63 parts per million. That's going to be the one that's directly attached to the electronegative oxygen. And I'm not saying don't look at that table in your book, but I think if you do, you'll see that's a very typical chemical shift for an alkane carbon that has a single bond to oxygen. And that's what you'd see typically in either an alcohol or an ether or something like that. So that's a very, very typical chemical shift for such a carbon atom. So other than that, I think you'll agree this spectrum is completely consistent with that structure. And again, I've put an old exam on eCampus so you can get an idea of at least potentially what sort of questions I might ask and what the format will be. I don't promise yours will be exactly the same, but between that and the practice that you get on OWL, and of course, hopefully by looking at a bunch of spectra on that one website, I think my hope is at least that you'll get an idea of what to look for in these and how to interpret them. The next one we have here is 3-methyl-3-pentanol. And so let's see here. Seem to be struggling at the moment. (3-methyl-3-pentanol). There we go, something like that. And now, if we figure out how many different types of carbon there are, Well, I think you'll agree that these two methyl groups now are the same. And the way you know that is because they both have the same types of connectivity. They're both connected to CH2s, and those CH2s in turn are connected to this unique carbon over here, which is connected to the OH in another methyl. So those two methyls are the same as each other, but different from this methyl. The way you know that is again by the connectivity. This methyl carbon is directly attached to the carbon that has the OH on it. These two are not. They're attached to CH2s. Of course, the two CH2s are equivalent to each other also. So there's one type of carbon over here, that's these two methyls. These two CH2s are another. There's this methyl group, which is a third type of carbon. And then there's this quaternary carbon that's directly attached to the OH. That's its own animal also. So I count 4 types of carbon in this molecule. And again, that's exactly what we see on the spectrum, 4 peaks. I would expect, again, that we'd see the most downfield one being, of course, this carbon here that's directly attached to the oxygen in the OH group. That one's going to be the most deshielded by the oxygen. It is interesting that we see 2 taller peaks and 1 shorter peak. I don't know that I'd bet the farm on that, though it is typical for taller peaks to correspond to those that there are more of. So I would expect that the 2 peaks here, at least my best guess would be, they correspond to the methyl and the CH2 that are in the ethyl group, with the CH2 being closer to the oxygen, so it should be further downfield, the methyl group further upfield. And then perhaps this shorter peak here is the methyl group over here. So that's one thing we notice. We also notice that oftentimes, but again, it's not an always type of thing, but oftentimes the height of the peak is also proportional to the number of hydrogens directly attached to that carbon. That's often true, other things being equal. Maybe not 100% of the time, but probably 85 to 90%. And it's okay if something's not true 100% of the time. It's still a rule that you can trust. It's a pattern that you can trust. So that would be how I would assign those peaks. But regardless, I think we have a spectrum that's totally not surprising given the structure. What if we started introducing some unsaturation? This one here is the spectrum of cyclohexanone, which I bet you could draw. Maybe we haven't officially learned how to name ketones yet, but cyclohexane, cyclohexanone, right, no big surprise. I think you all would have guessed that that's the structure. So now how many types of carbon do we have? Well, we have the unique carbonyl carbon, of course. We'd expect that one to be the furthest downfield, furthest to the left of the spectrum, because it's attached to an electronegative atom. And then we've got this type of CH2. There's 2 of them. Those are the ones, one away from the carbonyl. We could say alpha to the carbonyl group. Then we have these 2 CH2s, which are different from those, but the same as each other. And then there's this unique CH2 that's in the opposite side of the ring. So I count 4 types of carbon. There should be 4 peaks. Lo and behold, there are 4 peaks. Of course, this one down at, I almost want to call that around 215, that's going to be your carbonyl carbon. And that's very typical of where we would see a carbonyl carbon on a ketone or aldehyde. Maybe somewhat further upfield if you had an ester or carboxylic acid, but ketone or aldehyde carbonyl carbons are very, very far downfield. They're pretty much as far downfield as you ever see anything showing up. Meanwhile, we've got these other 3 types of carbon over here, and they're all of the alkyl type carbons. I would expect that of these 3, the most downfield one, this one around maybe 41 parts per million, would be those CH2s that are alpha to the carbonyl, next to the carbonyl, and that's a very typical place for those to show up. The other 2 would be those that are those 2 types of carbons that are further away from the carbonyl. And would I guess that the shorter peak is the CH2 that's unique. There's only one of them. And the taller peak is the CH2 not next to the carbonyl, but that there's two of? Yes, I would. That would certainly be my guess. And I would expect that my guess is correct there. So I left as an exercise for you that will get you started in thinking about NMR spectra. What if we started putting methyls into this and breaking the symmetry in the molecule? Of course, if we added a methyl on carbon 4 like this, there's still a plane of symmetry running down the molecule. So instead of seeing 4 peaks, I expected we'd see 5. There'd still be another peak for this methyl group, but there's still a plane of symmetry, right? Those two CH2s are still the same. Those two CH2s are still the same. But if the methyl were on a different carbon from carbon 4, then you would break the symmetry, and you would get more types of carbon that are different, and you would expect to see more peaks on the carbon NMR spectrum. So that would be something good for you to work out on your own. Here we've got trans 2-octene. Just wanted to show you an example of an alkene. And octene, 6, 7, 8. Was it trans 2-octene? Yes, so we'll put our double bond over there. So there's your trans 2-octene. Well, the most downfield carbons are, of course, going to be these two alkene carbons. And they're at like 124 and 133 or 2 parts per million, something like that. Very typical range for alkene carbons. The remaining 1, 2, 3, 4, 5, 6 are all going to be clustered together up here. And I think we could just barely make them out. 1, 2, 3, 4, 5, 6. You know, I mean, the resolution does sometimes work a little bit against us, but I think that looks well enough like there's 6 peaks there. As to which of those is which, I would not be too fast to predict, except I would think maybe that these two that are allylic, that are next to the alkene, those might be the two that are furthest downfield. It's a reasonable guess. Even as to which of these two alkene carbons is which, I don't know that I would be comfortable hazarding a guess. But I will say that we would have expected all 8 carbons to be different, that these two are going to be your 2 alkene carbons, your remaining 6 aliphatic carbons would be up here somewhere. Other than that, I don't think there's too much that we can learn from this. One question I often get asked here is, what would cis-2-octene look like? And my answer is, I bet it would look very similar, but not exactly the same, because it isn't the same compound. So I don't expect that those would fall exactly on top of each other. Look it up. You might be able to find the spectrum of that, but I bet that's what you'll find. In terms of telling them apart, I wouldn't presume. I don't think that's something that we could do just by the carbon NMR. Proton NMR, yes, those would be very different. So that will come later on in the term. So that's a typical alkene over there. Over here, we've got a typical aromatic compound. This is parachlorobenzaldehyde. Whoops. I think you could probably figure that out. You know what benzaldehyde is from us looking at aromatic compounds. Benzaldehyde is, of course, benzene with an aldehyde group. And it's parachloro, so that means there's a chlorine in the 4 position. Right about there. And so there's our structure. What would we expect to see? I'm not looking at the spectrum. Well, we've got our aldehyde carbonyl. That would be by far the most downfield. We've got this one that's directly attached to the carbonyl of the aldehyde. These 2 carbons are the same as each other. They're both ortho to the aldehyde and meta to the chlorine. These 2 also are the same as each other. They're ortho to the chlorine and meta to the aldehyde. And then, last of all, there's this unique carbon that's attached directly to chlorine. So I count 1, 2, 3, 4, 5 types of carbon. And bingo, that's exactly what we've got. Once again, our carbonyl carbon is the most downfield one. Let's say that's at 191 parts per million. Very reasonable place for an aldehyde carbonyl carbon to show up. Meanwhile, we've got two tall peaks and two short peaks in the aromatic range. And they're round about there, 130, 140, 150, very typical for aromatic carbons. My guess would be that the two taller peaks are going to be the two types of aromatic carbon that have hydrogens directly attached, and the two shorter ones are going to be the one attached to chlorine and the one attached to the aldehyde group. Beyond that, I would be hesitant to say exactly which is which, but I think based on this already, you can see the structure and the spectrum are completely consistent with one another. I guess that's actually the last spectrum that I have for you here. But that at least gets us through the major kinds of functional groups, major types of carbons. I'll have to leave the rest for you to explore on your own. But I do want to get this video made and up on YouTube so that you have that at your disposal. We'll see what happens on Wednesday. Hopefully I'll see you on screen on Wednesday, but beyond that, stay safe.